Okay, so yes, Lasse, can you tell me again whether you can hear us?
Yeah, we are able to hear.
Yeah, okay, so you're here. Okay, yeah. So now we will do very important presentation. So we need to make sure that we have everything properly set and recorded. Okay, so can you go into Zoom, into same link? Yeah, this is this like one of key things you need to like absolutely definitely know when you start in like electronic company. You don't have to know like clock domain crossing or all the details of like skew, slew. Um, no, they will ask you about like setup and hold, so that you also need to know. But this thing, yeah. So let me put the screen sharing.
Yeah, thank you.
1 second. Where is the screen sharing? Here. Okay. Okay, so you can try screen sharing now. Yeah, and then like after this, you explain our like challenge 1 and challenge 2. These are formulas. And then we will tip about like challenge 3, which I'm going to use to show that AI still doesn't know how to do simple things. Okay, let's see. Okay, so first of all, let's make sure that everybody. Okay, so can you find a lab? Let's make sure like everybody runs FIFO. So you can go like labs, then to microarchitecture. Yeah, then go to FIFO. Then with the right mouse button, go to flip flop FIFO. We start. So this is number 4. 4 4 2 4 4 2 4. Yeah, this one. So just do with the right mouse button. Yeah, like open an integrated terminal. Yeah, then just with right mouse button you go to open an integrated terminal. I just want you to run this here. So if you go here, use the right mouse button, put open in integrated terminal, and then here you can just press 03. Stop, sorry. Is it working? No, can you press bash space? Yeah. What is it?
Okay.
Sorry, can you?
The bash one.
Yeah, this is the bash one. So let's just do. Yeah, this is.
Oh, this one isn't in the. That one.
So you need to go to directory.
Yeah.
Yeah. So just go to that FIFO one. I want everybody to run it because this will be much more easy for you to see both screen. Okay. So did you run FIFO example? So yeah. So this is called 424 flip flop FIFO. So go here. Put with right mouse button open in integrated terminal. Yeah, and then just press here 03. No, don't click here. Click here. So what you do here is that you like is this Windows machine? Or? Yeah. So you just do here like bash space 03, and you run this. Yeah. Then you connect it here. Oh no. You went to somewhere else. What is this? Oh. What? Wait, do you have bash installed? Git bash. Yeah. You have so it's not in the past. Okay. So you just here put cd to that directory. Yeah, so you have FIFO working. So press yeah, to this is to you just keep this button, so you keep this button and it just hears it, and then you remove and it like pops it. So this is push and pop. I want everybody to see push and pop. Yeah, so here you see you with this button you push into FIFO, and with this button you pop from the FIFO. Yeah, and that's it. So and then there is a second example with which is 425, which shows a layout. So then there is second example which shows layout things in memory. Okay, so you run it. So you will run two. Okay, so you have FIFO here.
I ran it, but
You need to 66. Wait. Let's go up.
yeah.
Stop. This is 10 nano 9K LCD. Yeah, 66. Yeah, let's put 66. Mhm. Okay, so just they connected. Yeah, I want to see everybody FIFO on. Want to see everybody FIFO on. Okay, so you can also put it. It's fine. Yeah. So, what about you?
Oh, I'm happy.
Ah, okay, that's fine. Uh-huh. So FIFO?
Yeah, I can run it.
Okay, good. Huh?
Okay, yeah, I can port multiple ports. I have this one. I have it, but you said you have the DE10.
Yeah, I will give you them.
Okay.
Yeah. Oh, wait. Yes, G10 is also like existing port.
Okay.
So do you have a
I
G10?
Yeah, I have a DE10 A700T,
Uh-huh.
and then I have a Basis 3, and I have this board.
Yeah.
Those are the
With
four I have.
with the G10, I can show you how like it runs right now. Okay, so I see that most of people have this 5.4, and then once you play with this example, you also need to play with examples that shows memory layout in 5.4. Okay, so like Alex, let's start. Yeah. But let's check that the cluster can hear you in a like in a microphone. So your microphone is connected, right? Yes. You need to be wait, you're like accepted, right? Yeah, you're accepted. So you need to like unmute yourself. Okay, so can you say something?
Okay, can you hear me?
Yeah.
Yeah, okay. So I'm just gonna walk through how a FIFO works. Like, so how many of you know like what it's for? Basically, it's a buffer, acts as a buffer, and you can store a bunch of data in a FIFO and then read it out like whenever you need it, right? Okay. And yeah, I'll just walk through like an example of how a FIFO might work. So what? Okay, so in the beginning, the FIFO will be empty, and then you'll have a read pointer and a write pointer. And basically, these are the pointers that will tell you like where you're writing to and where you're reading from. And on the rising edge of a clock, you can write if it's not full or read if it's not empty. So for example, right now, since the FIFO is empty, you can't read from it because there's nothing to read, right? And let's say, for example, you want to push a data into the FIFO, then the data at index 0 will be valid. You'll have a valid data at the 0th index, right? Okay, now let's read from it. So now the read pointer and the write pointer are on the same index. I'll talk more about that later, but you can see that data 0 is now invalid. You can't read. It's left the FIFO already. So that's why I put it red. And the FIFOs are also empty. Okay, and then
Let me just quickly interrupt you. So what you see on the board is two views of FIFO. So right now, Alex is talking about data location in memory. So a pointer is an index, and he shows how it's actually located in memory, but this is not in our example of 424. What he's showing, you will see in example 425, because there are two views of FIFO. One is logical and another is like physical. So logical, from logical point of view, you push it and it goes to the head like data 0, and then data 1 goes, and then you pop and remove from here, and they're like gone. But in this case, you put data and then you move pointers. But when you listen to his presentation and look to 424 and 425, you can see how this all works together. Okay, yeah. So let's
Okay.
continue.
And then to fill the FIFO, we can just keep pushing into the FIFO. So we'll just keep pushing. And then once okay, this is a FIFO with a depth of eight entries, right? And the pointer will count from 0 to 7. And once it reaches 7, it'll loop back to 0. Okay. And then right now there's 7 entries in the FIFO. And then we have space for one more because it has a depth of 8. So we'll push another one into the FIFO. So now we have a full FIFO. Okay. And at this point, since the FIFO is full, you can't push into the FIFO anymore. And then now we can just read. And then you'll read data 1 out of the FIFO. And then you can also keep reading. And then same thing, pointer reaches 7, it'll loop back to 0. And then you can read one more time till the FIFO is empty. Okay. Is anyone confused like how that works?
So when the right pointer equals the read pointer, it's empty.
Okay, I'm gonna talk about that.
Okay.
Good question. Good question. Okay. Oh, and then this is also another example. Like you can read and write at the same time, as long as there's a data in the FIFO to read. So you increment both pointers. And then data 1 goes away, you have a new data 2. Okay, so how do you tell if it's full or empty when because the right pointers and the read pointer is the same, right? Okay, do you have an idea? Yeah.
One is red and one is green, so it could be like
Okay, but how do you tell like with logic? Yeah.
I mean the right pointer gets the read pointer, then it's full, the read pointer gets the right pointer, then it's empty.
Yeah, okay. Do you have a guess as to how you would implement this?
Okay. No, you go ahead. You got it. Okay, I was thinking
Once you fill up once, then you
overflow.
that's how you know when you started. But before you completely filled up, you know if you're empty.
Okay. So, okay. Then let me ask you if let's say they both overflowed. Okay. So right now right pointer is at 1. Okay. Index 1. And then read pointer is at index 7 or index 0. Okay. Actually, sorry, scratch that. Let's say they both overflowed once. Okay, so now right pointer is 1. I mean you have like an overflow bit, right? So they're both 1, and then they're in the same index. They're both pointed at the same index. Is it full or empty?
Empty.
Empty, right? So how would you fix that? Because you have an overflow bit, right?
Yeah.
So okay, basically the solution is to, as you said, you add an extra bit, and then you'll know basically you can count which cycle it's on. So as long as the pointer, they're on different cycles, it'll be full when the pointers are the same. And then When they're empty, it's when they're both on the same cycle and then the pointers are equal to each other. Okay.
So you have to keep like a cycle track of this.
Yeah, exactly. Okay. Anyone have any questions on that? Yeah.
No.
One bit.
This is a flag, even odd cycle. By the way, I make a comment here. So because I interview like a lot of students, and because at some point they want to show FIFO, they first of all, like if this is like online challenge, at least 1 year ago, some students were showing FIFO generated by LLM, which was using counters. So what was just counting how many things are present in FIFO and to distinguish full from empty. This is like a naive solution which was popular like in 90s, but you don't need counter because counter consumes like multiple, and especially like if you FIFO is large, it doesn't make sense. So what Alex is saying is like optimal thing, like odd or even cycle for each pointer, read and write pointer. This like one thing. So you like if they're both even, it means this is FIFO is full. If oh no, sorry, if they're both odd, if they're both zero, FIFO is empty. If they are both even, FIFO is empty, but if one even and another is odd, then FIFO is full. It means that like right pointer already made like n plus 1 number of circles, and read pointer made just n. So now right pointer catches read pointer, and FIFO is full. Now there is a interesting mistake, like interview mistake. Many students, for whatever reason, they could use FIFO should have depth of power of 2. Even here, so we have 8. And like as a result, many students, when you need like only FIFO of depth 5, they still put 8. And this is actually then some of them read article of Cliff Cummings, who shows that in order to detect whether it's full or empty, he put additional bit for each pointer. In which case, here we need only 3 bits, so 3 bits have 0 from 0 to 7, and he put 4 bits. And then he does like increment, and when it overflows from 7, it just goes to 8, which is 1 0 0 0, and uses this extra bit as a sign whether it's odd cycle or like even cycle. But the problem is that this does not work when depth of FIFO is not power of 2. So when it's 5, this whole scheme breaks. So when student write like during interview, which assumes power of 2, this is not going to work if FIFO depth is not power of 2. Now there are many people, like especially with like primarily software background, who are saying, why don't we make always power of 2? Because it's like simpler. You don't need to put additional condition for circling pointer. And the answer is that in hardware, you need to waste your flip-flops very carefully, because flip-flops contribute most of power, like in circuit. And in things like core router, you have like a chip like previously was designing blocking, which is like Juniper core router, is a chip which like consumes several hundred watts. So basically, if you put all 5 for their power of 2, and 5 of there are very precisely figured out numbers of exactly linked to latencies of pipelines and so on. And if you put everywhere a power of 2, then all your FIFOs, both SRAM based and flip-flop based, all these FIFOs will be like on average like 1.5 times larger than they should be. As a result, now you consume like X 100 watt, and now you consume 1.5 X 100 watt, and you need liquid cooling, which makes device very expensive. Same thing for phones. If you put everywhere 5 was power of 2, your battery will die soon. So for this reason, you shouldn't put, like, especially like during interviews where you have parameterized FIFO, you should make sure that you have a condition for pointer, that you circle back pointer when you check that pointer is at position depth -1. You shouldn't always assume that this is power of 2 and just after 7 will go back to 0 when you put +1. Yeah, okay, so let's continue.
Okay. So that's basically how a FIFO works, and now we're gonna see how we can use it in a challenge.
But before this, let's run both example. One is 424 and 425. So in 425, it shows actually what happened with the pointers in memory. So just run 425, also press buttons 0 and 1. Yeah, and you can do this while Alex.
Okay.
Let's see.
Okay. So basically the challenge goes like this. You have you want to write a pipeline block that computes a formula, a fully pipeline block. So that means it'll be outputting one data every cycle, every single cycle, as long as you're feeding inputs into the machine. Okay. And to do this, you're only allowed to call or instantiate the Wally FPUs that you're given, some provided modules. So you don't know how it works, but you have to figure out how it works basically. And that's part of the challenge. And are you guys familiar with AXI streaming handshakes? Okay. So your design also has to follow like a basic handshaking protocol, which is the valid, ready, and then data protocol. And when you receive back pressure, your design has to pause. But once the back pressure is lifted, you have to be able to keep sending out your data without any bubbles. Yeah. So back pressure is when your downstream module can't process data as fast as you're sending it. So
this is essentially stall in so you learn like RISC-V CPU, right? So back pressure is same as stall. So basically ready signal is saying that now like not ready to accept is same as in your CPU. When you have stall, it means that instruction cannot go to the next pipeline stage. So it needs to stay there until store is 0 and here until ready is 1. That's it.
right. And then after you're done with your design, you have to test it. You have to test it using a test bench that's also not written by you. So something that somebody else wrote. And you can check how it works, but you can't change it. Okay. I don't know if he wants you guys to try it, but I don't think we have time, so I'll just like walk through the solution. Maybe we can like try to work through it together. Yeah, okay. Okay. Yeah, so this is like what you're not allowed to do, or else the challenge would be pointless. Instead, you have to find the IO of the module and then instantiate it. Okay. And this is the AXI streaming. So back pressure, you see when T ready is not high, your T data is held for an extra cycle, right? Okay. And this is basically what I mean by bubble. So you see arg ready drops for one cycle because, I mean, there's a bubble. Yeah. And this is the log you get from running the simulation. And you can see that there's a bubble here. That's just one of the ways you can check for a bubble. The other way would be to open a waveform viewer. And this is when there's no bubble. Okay. So yeah, Anybody have any ideas of how we might approach the problem? So what can we do? What are the problems? Let's identify the problems first. Yeah.
Have valid data or valid like output every cycle.
Mm-hmm. Okay.
But then like the operation probably takes more than one cycle to do.
Right. Yeah. Okay.
Not right.
Okay. Yeah. Yeah. Okay. Okay, this is kind of hard to see if you're not like playing around with the files. But basically, when you instantiate one of the FPUs, you'll find that it doesn't give you the output, the result of your inputs, the computation, immediately. So maybe you'll feed in A plus B, and then it'll give it to you like 10 cycles later, but you don't know how long later, how many cycles it'll take for you to get your output, right? So the first thing you have to do is to find the latencies of the submodules, okay? And to do this, we'll kind of modify what's given. So we have a test bench, and then basically it takes inputs A, B, and C, and then we can modify it to do, it drives the inputs A, B, and C. And we can change it to drive only 2 inputs, and then also change the design under test. So the module that we're testing. So I modified it, I changed it. Oh, this is kind of hard to see. And then you also have to be careful because you can't just change the DUT. You also have to change like all the IO to match the module that you're testing. And once you run the test bench, you'll see that you can count how many cycles it takes to get an output. So you'll see that on cycle 369, you receive an input of 000 or 0 and 0. And then on cycle 372, you'll get an output of 0 times 0 is 0. Same thing with cycle 370. You'll get it at cycle 374. So 1 times 10 is 10. And then you can do it for all three of the modules that we need, because we don't have a power module, exponential module. So I found that the fmult is 3 cycles. The latency of fmult is 3 cycles, fsub is 3 cycles, and the fadd is actually 4 cycles. And what's nice about this is that all 3 of these are pipelined. That means like as long as you're feeding inputs, it'll be processing like more than 1 data at a time, right? More than 1 output at a time. But for the division module, that's not the case. So it's not pipelined. You can only do 1 at a time. Okay, so now that we know the latencies, does anybody want to try designing like an architecture to just make a architecture that can compute this formula? And the formula is this: a to the 5th plus 0.3b minus c. Yeah.
Best I can explain is like you multiply A with like you store A into like a register or something, and then you multiply it by that register 5 times. So it's like, and then you just feed that in each other, like you chain it,
Mm-hmm.
and then you chain that output, and then at the same time, you have the 0.3 times B like happening,
Mm-hmm.
and then this minus C can have, and then you minus C with the 0.3 times B because it's faster, and then you add that with the.
Yeah, okay, that's exactly how you do it. Nice. That's exactly what you do. So first we'll multiply A by itself. You'll get A squared. and then you'll get a squared on cycle 3. And then you multiply a squared times a squared to get a to the 4, right? And then you'll get that on cycle 6. And then you can multiply by a again to get a to the 5th. But we have to be aware that a is always changing. It can always be changing, right? So we need to make sure that the a to the 4th, the a in a to the 4th is multiplied with the same a like by itself. So to do that, we'll use something called a ring buffer, which basically what it does is you'll send in some data, and then after a fixed amount of cycles, it'll spit out the exact same thing.
Yeah, the functionally equivalent to shift register, but uses pointer inside.
So it saves power. Okay. And okay, as you said, we'll do the 0.3b minus c in parallel. So this is what we'll get. And then same thing, we'll have a ring buffer to align the 0.3b, the result of 0.3b and c. So we can subtract those two. And then we'll also need that result to end up on the same, to match the cycle of the a to the 5. So we'll put another ring buffer there to make it align on cycle 9. Okay, and then after that, we can just add them. So we'll have a total pipeline latency of 13, right? Because the latency of FAD is 4. So 9 plus 4, 13. Okay. Now that we have something that can compute the formula, we need to somehow solve the problem of adding the control flow. Because if you look in the files, the arithmetic modules, they don't have a valid ready. They only know when a data is valid, but they can't block a data from entering. Okay, so to do this, we'll use something called a credit counter. Or we need a valid ready data, valid ready first. But the problem is this pipeline we have right now, you can't stop it. So every cycle, the output of that pipeline will disappear. So we need to find a way to store this output, right? So to store the output, we'll use a FIFO. And yeah, we'll use a FIFO, and then but the problem is that we won't know when to stop. We still don't have the valid ready handshake. So to solve that problem, we'll use something called a credit counter. And basically how the credit counter works is you start with a fixed amount of credits. And if you receive an input, you lose a credit. And then if you send out an output, you get refunded a credit. And once you hit 0 credits, you're stuck. You can't do anything. You can only send outputs and to refund a credit. Okay. And now the problem is we need to find out what the depth of this FIFO should be. Okay. Does anybody have any guesses of how deep this FIFO needs to be? Yeah.
Handle like the worst case scenario, so like as long as how many cycles it takes to complete one.
Yes, exactly. Yeah. 13, but you have to keep in mind that the FIFO itself has a latency of 1. So it's going to be 13 plus 1, which is 14. And then since your FIFO has a depth of 14, you also need 14 credits. So that's how you get the credit depth, or the credit number of 14. You'll start with 14 credits, and then you can keep accepting inputs until you run out of credits. Okay. And I can go over the code to do this. Yeah. So
By the way, there are examples for a ring buffer inside because there is a five. So we have examples. There is a shift register is ring buffer and is five. Five uses 2 pointers, ring buffer uses 1 pointer, and shift register just moves data. Yeah, and you can also look to code in examples how shift register, ring buffer, and five organized. Yes, that will show how they're used. Yeah, but maybe you can go through code yeah, let's go through code for ring buffer. This is one of my interview questions, by the way. So when students write something in shift register, I ask them how to make it low power, and then some small percentage of students know what ring buffer is. So most of students know shift registers, FIFOs, but with ring buffer, I ask them to write to code ring buffer. So this is something useful to note, but you can see it working on the board. You have it together.
okay, so basically how the ring buffer works is similar to a FIFO. You'll have a pointer that points to where you want to write data, but in this case, for this ring buffer, we'll use the same pointer to read data. Okay, so you'll see that when
Excuse me, Alex.
basically on a clock edge, you can push a data into the ring buffer, and then you can also read the
Hello,
data out of the ring buffer. It's if you just look at the code, you'll understand.
excuse me, Alex.
And one thing that you have to be aware of is that this d out, this data that you're pulling out is not synced to the clock. So the data being pushed into the ring buffer can only be pushed on a rising clock edge. So that's why it's put inside a flip-flop block, always F block. And the data that you're reading out, you can read out anytime. So it's kind of perfect because once you read the data out, you'll push a new data into the same position. And yeah, you can parameterize the data width and the depth of the ring buffer. So, and the depth is basically the latency of the ring buffer. Okay. And this is basically this architecture that we built earlier. It's really easy. You find the module that you want to instantiate, and it's literally just connecting wires. So we'll have one mult block for a squared, another one for a to the 4, and then another one for a to the 5th. And you're just basically kind of like the picture that I drew. You're literally just connecting wires. And that's like the fun or easy part. Fun in my opinion, compared to like CS where you have to like actually think. But here you could just like connect wires, you know. It's kind of like connecting the dots, to be honest. And yeah, we'll also add the ring buffers, literally just connecting wires. Okay, and this is how the flip-flop works, the FIFO works. You can see that here. Okay. So this part at the
Excuse me.
top, you're basically updating the right pointer. So whenever you push, you can increment the right pointer, and then oh, this is not. Oh, this is This is updating the cycle counter. So when the pointer reaches the max and then it's looped back to 0, you'll change the you'll negate the right pointer or the cycle. So it'll change from 0 to 1 or 1 to 0. And then you can also and then you can also increment the right pointer. So it just counts up until the right pointer is equal to the maximum, your depth, and it'll reset back to 0. And then same exact thing for the read pointer. And here this is how we update the FIFO. So we'll have some type of storage. In this case, it's called data. So once if we're pushing a data into the FIFO, you have to push it like using a non-blocking statement, right? And then similar to the reading from a ring buffer, you have to read you can read the data anytime as long as it's not empty. As long as there's something to read, you can read the data anytime.
The buffer, you're saying it's not clocked?
The writing, the pushing is clocked, but the read is not.
Oh, okay. So it's always pushing, but the read's async. You just
Yeah. Whenever you want, you can just read. But here, like you need to update the read pointer. So that's like how it's a little different from the ring buffer. And this is the logic to check if it's empty or full. So basically, when the pointers are the same, when the pointers are the same and then they're on different cycles, it's gonna be full. And then when everything's the same, then it's empty. And this counter thing, you don't need it for like a basic FIFO. Okay. And now we just connect everything again. So we have our pipeline that we named challenge without flow control. So it'll have some inputs and outputs, and we need to add the ready signals to handle the back pressure. Okay. So first we just instantiate that whole thing that calculates the formula for us. And we need to also instantiate the FIFO, which will help us save the data that's coming out of the pipeline. Yeah, and you're literally just connecting lines here again. Not much to say about this, it's just connecting wires. And here is the credit counter. There's actually logic for this. Basically, you'll start with so pipeline depth, which is 13 plus 1, 14 credits. And whenever you accept a new input, so this is a case statement. Does anybody know what like this is? Oh. Does anybody know what this is?
They learned the syntax of Verilog, so this thing they know. So just
Okay.
you got 2 bits and check with this 1001.
Yeah. Basically, it's like a sensitivity list. And whenever either pipe arg valid or FIFO pop changes, then you'll go into this case statement and update the the new credit, the credit count. So if the pipe arg valid is high, then you lose a credit. If it's the other way around, you get refunded a credit. But if they both change, you'll see there's no case statement written here. But since, yeah, so the credit will stay the same because you're both losing a credit and then getting refunded a credit at the same time. And yeah, that's basically how you handle the back pressure. Does anybody have any questions? Yeah.
Wait, so this entire problem, was it done like live or?
Live? No, not live. But I think once you get used to it, you should be able to do it in like max 2 hours.
Not too bad to say like 10 minutes.
No. But that's also because like we know the solution now, right? So if you went home and you wanted to do this, you should be able to do it pretty quickly. Yeah.
How long did it take you to first go around to figure something like this out?
Took me like a week because I wasn't using this credit counter. I didn't know about this credit counter yet. So yeah, I had a different solution. But this is like a optimal, I guess, solution. And yeah, that's basically it.
Yeah, this is actually funny that even like Intel in their like educational materials, they actually don't use credit counter. They just recommend to keep to always keep extra space in a FIFO in order to drain everything in your pipeline. But the problem is that you just waste your FIFO when there is no transactions flying into pipeline. So suppose there is no transactions flying, can you apply back pressure? Then you will just waste of clock cycles. But like all like, but this is because those like materials are created by their like educational department, like manager of educational program, not like design engineers. Because design engineers everywhere in like NVIDIA, Apple, and Samsung, Juniper, they all very well know this scheme. But if you go to like Apple, they can ask you very more complicated questions. This is like basic case. They may ask you for partial credit return from multiple stages of pipeline, and even credit return when you do cross clock domain question. This is a very like elegant question of the station. Anyway, yeah. So thank you. So now we have a review of basic necessary things you need to know when like doing like job interviews. So about like timing, about basics of microarchitecture, like FIFO pipeline. If you mention credit-based flow control in like any like large like electronic companies, they will love you instantly because they get used and got a little bit sick and tired that they need to explain to all students this in their first months as working in a company. And if anybody have like any questions, let's pack everything and move out of here. You can ask me. So if somebody want to buy board, you can buy a board. Like I will also leave some boards so you can put these things together. And you can contact me with email like if you have any questions. So yeah, if you're like interested in like Samsung internship, both in general, like with the Foundry or like within our group, you can also send me like email. So like I already recommended Alex to our director of GPU for such like internship. Yeah, but we like I'm not sure how much we got like this year, but in previous years we were getting intern, and one intern who created custom FPU, which actually inspired this challenge. He was intern like 5 years ago, and then he was hired on permanent position, got promoted to senior engineer, and his design he did during internship went into tens of millions of telephones. So such things are not just some toy. Oh, sorry. Yeah, they actually have practical significance. Yeah. Okay.
Thank you.
Mhm. All right. So let's finish everything.
All right, everybody, if you have like drinks and stuff, please use like outside food and stuff. You know, beans at the library also. Please clean up. Take your time
Yes.
outside.
Thank you, Yuri.
Okay. Thank you. Bye bye.